In evolutionary biology, the Baldwin effect describes the effect of learned behavior on evolution. In brief, James Mark Baldwin and others suggested during the eclipse of Darwinism in the late 19th century that an organism's ability to learn new behaviors, e.g. to acclimatize to a new stressor, will affect its reproductive success and will therefore have an effect on the genetic makeup of its species through natural selection. Though this process appears similar to Lamarckian evolution, Lamarck proposed that living things inherited their parents' acquired characteristics. The Baldwin effect has been independently proposed several times, and today it is generally recognized as part of the modern synthesis. A new factor in evolution. The effect, then unnamed, was first put forward in 1896 in a paper A New Factor in Evolution by American psychologist James Mark Baldwin. The paper proposed a mechanism for specific selection for general learning ability. As Robert Richards explains, if animals entered a new environment or their old environment rapidly changed those that could flexibly respond by learning new behaviors or by ontogenetically adapting would be naturally preserved. This saved remnant would, over several generations, have the opportunity to exhibit spontaneously congenital variations similar to their acquired traits and have these variations naturally selected. It would look as though the acquired traits had sunk into the hereditary substance in a Lamarckian fashion, but the process would really be neo-Darwinian. Selected offspring would tend to have an increased capacity for learning new skills rather than being confined to genetically coded, relatively fixed abilities. In effect, it places emphasis on the fact that the sustained behavior of a species or group can shape the evolution of that species. The Baldwin effect is better understood in evolutionary developmental biology literature as a scenario in which a character or trait change occurring in an organism as a result of its interaction with its environment becomes gradually assimilated into its developmental genetic or epigenetic repertoire. Simpson, 1953, Newman, 2002. In the words of Daniel Dennett, thanks to the Baldwin effect, species can be said to pretest the efficacy of particular different designs by phenotypic, individual, exploration of the space of nearby possibilities. If a particularly winning setting is thereby discovered, this discovery will create a new selection pressure. Organisms that are closer in the adaptive landscape to that discovery will have a clear advantage over those more distant. An update to the Baldwin effect was developed by Jean Piaget, Paul Weiss, and Conrad Waddington in the 1960s-1970s. This new version included an explicit role for the social in shaping subsequent natural change in humans, both evolutionary and developmental, with reference to alterations of selection pressures. Examples: suppose a species is threatened by a new predator and there is a behavior that makes it more difficult for the predator to kill individuals of the species. Individuals who learn the behavior more quickly will obviously be at an advantage. As time goes on, the ability to learn the behavior will improve, by genetic selection, and at some point it will seem to be an instinct. Baldwin gives the following case involving cooperation. Animals may be kept alive, let us say, in a given environment by social cooperation only. These transmit this social type of variation to posterity, thus social adaptation sets the direction of physical phylogeny and physical heredity is determined in part by this factor. Baldwin, 1896, p. 553. The appearance of lactose tolerance in human populations with a long tradition of raising domesticated animals for milk production has been suggested as another example. This argument holds that a feedback loop operates whereby a dairy culture increases the selective advantage from this genetic trait, while the average population genotype increases the collective rewards of a dairy culture. Controversy and acceptance. Initially, Baldwin's ideas were not incompatible with the prevailing, but uncertain, ideas about the mechanism of transmission of hereditary information, and at least two other biologists put forward very similar ideas in 1896. In 1901, Maurice Maeterlinck referred to behavioral adaptations to prevailing climates in different species of bees as what had merely been an idea, therefore, and opposed to instinct, has thus by slow degrees become an instinctive habit. The Baldwin effect theory subsequently became more controversial, with scholars being split between Baldwin boosters and Baldwin skeptics. The theory was first called the Baldwin effect by George Gaylord Simpson in 1953. Simpson admitted that the idea was theoretically consistent, that is, not inconsistent with the modern synthesis, but he doubted that the phenomenon occurred very often, or if so, could be proven to occur. In his discussion of the reception of the Baldwin effect theory, Simpson points out that the theory appears to provide a reconciliation between a neo-Darwinian and a neo-Lamarckian approach, and that Mendelism and later genetic theories so conclusively ruled out the extreme neo-Lamarckian position that reconciliation came to seem unnecessary. In 1942, the evolutionary biologist Julian Huxley promoted the Baldwin effect as part of the modern synthesis, saying the concept had been unduly neglected by evolutionists. In the 1960s, the evolutionary biologist Ernst Mayr contended that the Baldwin effect theory was untenable because the argument is stated in terms of the individual genotype, whereas what is really exposed to the selection pressure is a phenotypically and genetically variable population. It is not sufficiently emphasized that the degree of modification of the phenotype is in itself genetically controlled. It is assumed that phenotypic rigidity is selectively superior to phenotypic flexibility. In 1987, Geoffrey Hinton and Stephen Nowlin demonstrated by computer simulation that learning can accelerate evolution, and they associated this with the Baldwin effect. Paul Griffiths suggests two reasons for the continuing interest in the Baldwin effect. The first is the role mind is understood to play in the effect. The second is the connection between development and evolution in the effect. Baldwin's account of how neurophysiological and conscious mental factors may contribute to the effect brings into focus the question of the possible survival value of consciousness. Still, observes David Depew, it is striking that a rather diverse lot of contemporary evolutionary theorists, most of whom regard themselves as supporters of the modern synthesis, have of late become Baldwin boosters. These Baldwin boosters are typically evolutionary psychologists who are searching for scenarios in which a population can get itself by behavioral trial and error onto a hard-to-find part of the fitness landscape in which human brain, language, and mind can rapidly co-evolve. They are searching for what Daniel Dennett, himself a Baldwin booster, calls an evolutionary crane, an instrument to do some heavy lifting fast. According to Daniel Dennett, recent work has rendered the Baldwin effect no longer a controversial wrinkle in orthodox Darwinism. Potential genetic mechanisms underlying the Baldwin effect have been proposed for the evolution of natural, genetically determinate, antibodies. In 2009, empirical evidence for the Baldwin effect was provided from the colonization of North America by the house finch. Comparison with genetic assimilation. The Baldwin effect has been confused with, and sometimes conflated with, a different evolutionary theory also based on phenotypic plasticity, C. H. Waddington's genetic assimilation. The Baldwin effect includes genetic accommodation, of which one type is genetic assimilation.
Please subscribe and thanks for watching.